once.
Grr. This isn't working. Come on. Come on. Work. Show up. Be recognized. Gotta recognize.
I guess that means that out here we have zero probability. So these were our initial beliefs about the outcome of the experiment. Suppose now that someone comes and tells you that event B occurred. So they don't tell you the full outcome of the experiment, but they just tell you that the outcome is known to lie inside this set B.
I don't want to draw that like basically like B is like 1/2 in total. It's like B. A is like 5/6. So you know that B happened. Yeah, you know that B happened. So this whole side where it's kind of like A and it stretches over a little bit, like this side didn't happen. Usually when I draw these out, I just kind of do what he does and kind of circle this, but it's almost kind of nice to just be like, all right, this side just doesn't exist anymore. So B happened.
Then you should certainly change your beliefs in some way. And your new beliefs about what is likely to occur and what is not is going to be denoted by this notation. This is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told
probability that the outcome is going to fall inside the set A. Probability that A happens. We have our random experiment. We get an outcome. And if this is A, then the outcome could either be, in A, or it could be, not in A. The probability of A is saying the probability that our outcome falls in A. The probability of A happening. Yeah, it's like a one-time thing. Okay.
we're sure that the event lies inside the event B. Now, once we're told that
the outcome lies in event B,
the outcome lies inside the event B. Now, once we're told this is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told and we're sure that the event lies inside the event B. Now, once we're told that
he said the event lies in the event B, it's the outcome lies in the event B. So, yeah, kind of like B. You got kind of like A over here. So our probabilistic experiment happened. The outcome happened. The outcome could be this, could be this, could be this. So the outcome happened. It's somewhere in B. And then what does that tell us about the probability of A happening now?
Outcome lies inside the event B, then our old sample space in some ways is irrelevant. We have a new sample space, which is just the set B. We're certain that the outcome is going to be inside B.
Just to kind of draw that again, like where we had kind of like B here, and then we had kind of like A. So B happens. And so we say that B happens. And so like everything else like outside of B is like gone. And like this is our new universe now. This stuff is gone. Not happening. So this is what we're looking at now.
For example, what is this conditional probability? It should be 1. Given that I told you that B occurred, you're certain that B occurred, so this has unit probability. So here we see an instance of the revision of our beliefs. Initially, event B had a probability of 2 plus 1/6. That's
probability. So we got A here. We got the probability of A. So the probability of A is like, nope, nothing out here. Only wondering what the probability, like if the event happens out here, nope, 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 yes. It's the probability that the outcome happens and it falls within A.
half. Initially, we thought B had probability 1/2. Once we're told that B occurred, the new probability of B is equal to 1. Okay, how do we revise the probability that A occurs? So we are going to have the outcome of the experiment. We know that it's inside B, so we will either get something here and A does not occur, or something inside here and A does occur. What's the likelihood that, given that we're inside B, the outcome is inside here? Here's how we're going to think about it. This part of the set B, in which A also occur, in our initial model was twice as likely as that part of B. So outcomes inside here were collectively twice as likely as outcomes out there. So we're going to keep the same proportions and say that given that we are inside the set B, we still want outcomes inside here to be twice as likely as outcomes there. So the proportions of the probabilities should be 2 versus 1. And these probabilities should add up to 0 because together they make the conditional probability of B. So the conditional probabilities should be 2/3 probability of being here and 1/3 probability of being there. That's how we revise our probabilities. That's a intuitively reasonable way of doing this revision. Let's translate what we did into a definition. The definition says the following, that the conditional probability of A that given that B occurred is calculated as follows. We look at the total probability of B, and out of that probability that was inside here, what fraction of that probability is assigned to points for which the event A also occurs? Does it give us the same numbers as we got with this heuristic argument? Well, in this example, probability of A intersection B is 2/6 divided by the total probability of B, which is 3/6. And so it's 2/3, which agrees with this answer that we got before. So the formula indeed matches what we were trying to do. One little technical detail, if the event B has 0 probability, then here we have a ratio that doesn't make sense. So in this case, we say that conditional probabilities are not defined. Okay, now you can take this definition and unravel it and write it in this form. The probability of A intersection B is the probability of B times the conditional probability. So this is just a consequence of the definition, but it has a nice interpretation. Think of probabilities as frequencies. If I do the experiment over and over, what fraction of the time is it going to be the case that both A and B occur? Well, there's going to be a certain fraction of the time at which B occurs. And out of those times when B occurs, there's going to be a further fraction of the experiments in which A also occurs. So interpret the conditional probability as follows. You only look at those experiments at which B happens to occur, and look at what fraction of those experiments where B already occurred, event A also occurs. And there is a symmetrical version of this equality. There's symmetry between the events B and A, so you also have this relation that goes the other way. Okay, so what do we use these conditional probabilities for? First one comment, conditional probabilities are just like ordinary probabilities. They're the new probabilities that apply in a new universe where event B is known to have occurred. So we had an original probability model. We are told that B occurs. We revise our model. Our new model should still be a legitimate probability model, so it should satisfy all sorts of properties that ordinary probabilities do satisfy. So for example, if A and B are disjoint events, then we know that the probability of A union B is equal to the probability of A plus probability of B. And now if I tell you that a certain event C occurred, we're placed in a new universe where event C occurred. We have new probabilities for that universe. These are the conditional probabilities, and conditional probabilities also satisfy this kind of property. So this is just our usual additivity axiom, but applied in a new model in which we were told that event C occurred. So conditional probabilities do not taste or smell any different than ordinary probabilities do. Conditional probabilities given a specific event B just for...
Yeah, if you kind of just do like probability of A union B given C, for instance, yeah, this is just a new probability distribution. So you could almost say like, I don't know, this is like the probability kind of given C of A union B. Like we're just subscripting the C here. It's, yeah, I mean, this is just a brand new probability law, whatever. Probability that the outcome falls within this set. We're going to do an outcome, and it can either be in this set or it could be not in this set.
A probability law on our sample space. It's still a probability, it's a different probability law, but it's still a probability law that has all the desired properties. Okay, so where do conditional probabilities come up? They do come up in quizzes and they do come in silly problems. So let's start with this. We have this example from last time, 2 rolls of a die. All possible pairs of rolls are equally likely, so every element in this square has probability of 1/16. So all elements are equally likely. That's our original model. Then somebody comes and tells us that the minimum of the 2 rolls is...
Kind of think about this with the, Yeah, we're talking about the probability of A given B. So given B, it's kind of like we got B, this is our new universe. And so given B, so we're kind of like in this universe now, everything else is impossible. And so now we're asking what's the probability of A? So you kind of, yeah, look at the intersection between A and B, the overlap. Yeah. You got this area. Yeah.
Equal to 0. What's that event? The minimum equal to 0 can happen in many ways if we get two zeros.